today's lecture is about pairwise independence. And before we get into the topic of pairwise independence, I'd like to remind you that the independence that we enjoy is expensive. It's both expensive for us in society, it's also expensive in computer science. Well, let's start with society because it's a little bit more interesting. And so here's a quote from Mahatma Gandhi. Freedom is never dear at any price. It is the breath of life. What would a man not pay for living? And in essence, he's saying the price of freedom is your life. I mean, you should be willing to give your life for the independence that we enjoy. And so that's tells you something. Independence, freedom, these are expensive things. And the other aspect, in a lighter vein, is that you may think you have independence, except you don't sometimes. And this again is true in computer science. We may think we have independent random bits, but maybe we don't. But here's a little cartoon, my favorite, Calvin and Hobbes, where you can pause and enjoy the cartoon. It talks about the perceived independence that Calvin enjoys in America, but is that true? It's for you to interpret the cartoon. So in some sense, you can think of a place as the very essence of independence and still question whether it's truly independent. And that's again true about random bits, because a lot of times we make our analysis, our life easy by assuming independence, but is there a good source of independent random bits? That's a tough question. So in this lecture, we're going to try to address this issue. And the way we're going to address it, we're going to allow random bits to be less than perfectly independent, and but still maintain some formal understanding of what we mean by that. And that way, we can still analyze our algorithms, our samplings, and things like that with some mathematical rigor. So that's the goal of today's lecture. So in some sense, we're going to look at random bits without the level of independence that we are used to. So just let's first remind ourselves what we mean by that independence. Recall that given two events E1 and E2, we say that they are independent if the probability of this event E1 intersected with E2 equals the probability of E1 times E2. Another way of stating this, recall, is probability of E1 given E2 times the probability of E2. Now that, if you recall, is nothing but probability of E1 intersected with E2. And if that equals probability, this whole left-hand side equals probability of E1 times probability of E2. Now here, probability of E2 can get cancelled out. So essentially what we have is that the probability of E1 given E2 equals the probability of just the event E1. So in other words, the probability, the fact that E2 happened or did not happen has no bearing on the probability of event E1. And by symmetry, we also have that the probability of E2 given E1 equals probability of E2 when events E1 and E2 are independent. So they're independent means here that whether E1 occurred or not has no bearing on the probability of event E2. Things become a bit more interesting when you have more than just two events to talk about. So let us consider some n events E1 through En. And we say that these n events are mutually independent if for every subset of 1 through n, basically a subset of indices used to denote these events. For every such subset, I, the probability of the intersection of all events E little I, where little I belongs to the set I, equals the product of the individual probabilities. And let me emphasize that this has to be true for all subsets I of the index set 1 through n. And of course, the notion of independence extends to random variables as well. So if you have random variables x and y, these two random variables x and y are independent if the probability that x equals to a particular value x and the probability that y equals to a particular value y, uh, importantly, for all x comma y in the ranges of values that x and y can take, the random variables x and y can take, if this probability on the left hand side equals the product of the individual probabilities, that is the probability that the random variable x takes the value little x times the probability that the random variable y takes the value little y, then we say that x and y are independent. Okay, and as one might expect, this notion extends to multiple random variables. So let's say we have random variables x1, x2, and so on up to xn are mutually independent. Again, if for every I that is a subset of the index set from 1 through n, and now for any values xi, where xi's fall within the range of the individual random variable, say uppercase xi, we have this this independence condition holding true, which is that the probability of this giant intersection over all these events, that is x1 taking the value little x1, x2 taking the value little x2, and so on, all these events intersected together equals the product of the individual probabilities. So if this condition holds, then these random this condition must hold for every I subset of n and for all combination of values xi in the range of the random variable xi for all I. So what we have seen so far is just a recollection of independence the way we know it. In particular, we're talking about mutual independence. And we want to relax this notion. And in order to do that, we have to modify the definitions just a little bit. So this slide, we've defined the mutual independence of events. Recall this. And now we want to suitably relax this notion of mutual independence. And in its place, we're going to define something called k-wise independence. And the key to defining k-wise independent events is to limit the level of independence. Now here, this independence condition given here must hold true for every I that's a subset of the indices from 1 through n, and that's the requirement for mutual independence. For k-wise independence, that's what we're going to relax. We're going to say that this independence condition has to only hold for subsets I whose cardinality is at most k. And when we impose that restriction on I, we get k-wise independence. And of particular importance will be pairwise independence, for which we will require the the independence condition to hold for all subsets of size at most 2. And as you can imagine, this notion of k-wise independence or pairwise independence quite naturally extends to random variables, independence of random variables as well. So there again, let's go in and make the necessary changes. So here we are interested in defining a set of random variables to have a limited form of independence. In particular, we want to, as we did with events, define these random variables to be k-wise independent. And as before, we want this independence condition to hold for all subsets I of the index set, and with the limitation being that the cardinality has that we care about is at most k. When the cardinality of this I goes beyond k, then we have no restriction on whether those events, those individual values for those many random variables obey the independence condition that we have here. Everything else stays the same. So every time we restrict our requirement of this independence condition to hold only for subsets of a certain size, at most k, then we get k-wise independence. And of course, as before, we can define our random variables to be pairwise independent if the independence condition holds for subsets whose cardinality is at most 2. You may wonder, why do we even care about pairwise independence? As it turns out, pairwise independent random bits are a lot cheaper in terms of the amount of randomness that we need to have in order to generate them. So what do we mean by that? Let us consider B mutually independent and uniformly random bits. Let's denote them x1, x2, and so on up to xb. From this, we would like to generate pairwise independent bits. And we would like to generate lots of them. In particular, we would like to generate an exponential number of them. Let's see how we can do that. Now consider these b bits, x1, x2, and so on up to xb. We know that the cardinality of the power set is 2 raised to the b. And if we get rid of the empty set from the power set, we'll have 2 raised to the power b minus 1 subsets of this set. And now take each subset. So let's say we take this subset as j, and using this subset as j, let's generate a random bit. We'll call that yj. And yj is simply the exclusive OR over all bits in Sj. So in this manner, we have now generated 2 raised to the b minus 1 random bits. But how random are they? Let's, for example, try to prove that they are uniformly at random. And now if we expand this out, we get something like this. xi1 exclusive ORed with xi2, exclusive ORed with subsequent elements in the sequence, bits in the sequence, and so on up to xi cardinality of S. So here's what we're going to do. We're going to isolate this one bit. Now if you consider all of these bits, all but the last bit, the exclusive OR of those bits is going to be either 1 or 0. Now what is the probability that yj equals 1? There are two possibilities. Either the first set of bits were all 1, their exclusive OR was 1, or their exclusive OR was 0. And for simplicity, let's call this event A and this event B. So the probability that yj equals 1 is equal to probability, the last bit is equal to 0 given event A times the probability of A plus, in similar fashion, the probability that the last bit is a 1 given event B times the probability of the event B. The fact that the original bits were independent means that these conditional probabilities we have written here, are really not conditional probabilities. So you can write them as unconditional probabilities. So the expression comes out in this manner in which it's written. But these probabilities, we know their values. They're just nothing but half each. So the expression simply becomes half times the probability of A plus the probability of B. Of course, the probability of A plus the probability of B is nothing but 1, leading to half. Of course, a similar argument will also help you see that the probability of yj equal to 0 is also going to be a half. So this idea of focusing on the last bit is called the principle of deferred decisions, which is a widely used technique that is well worth knowing. In fact, here's a little exercise for you. What we have shown so far is that these random bits, these yj's, are uniformly at random. But we also need to show that they are pairwise independent. And that's your exercise. For all I and j, prove that the yi's and the yi and yj are pairwise independent. And in fact, you can do this again using the principle of deferred decisions. So that's going to be your exercise. The question now is, can we do better? And as it turns out, we indeed can. And here's how we can do better. Let's consider the integers, the set of integers from 0 to p minus 1, where p is a prime number. And now from this set, let's draw x1 and x2, both uniformly at random. Okay, so we only need to draw two numbers from this set. And then with those two numbers, we generate p random numbers. Here's how we do that. Yi is the ith such random number, and we generate that by computing x1 plus I times x2 mod p. Okay. As it turns out, these yi's that we generate are are drawn uniformly at random from 0 to p minus 1. And moreover, they are pairwise independent. That's what we need to show. Well, let's see why that is the case. To begin with, let's prove that the yi's are drawn uniformly at random from F. Again, without much surprise, we end up using the principle of deferred decisions. Here we fix x2, okay, and then we observe the random variable x1, and recall that x1 is drawn uniformly at random from the set F. And under this context, it's easy to see that the yi's are going to be also drawn uniformly at random from F, because we take to whatever I times x2 that we have, we add x1, and then we take mod p. So the yi's are going to be drawn uniformly at random from F as well. The more interesting thing will be to prove that these yi's are pairwise independent. So how do we do that? Well, for a pair of indices I and j, ranging from 0 to p minus 1, we need to show that the probability that yi equals some specific value a and yj equals some other specific value b is exactly 1 over p squared. So this is what we need to show, and uh, let's see how we can prove that. We have to observe that the event that yi equal to a is equivalent to x1 plus I times x2 equal to a the whole mod p. Okay? And similarly, the event yj equal to b is equivalent to x1 plus j times x2 equal to b mod p. Okay. So what do we have here? We have two equations and we have two unknowns, and therefore there is a unique solution for x1 and x2, and recall that p is a prime number. So let's just fix x1 equal to lowercase x1 and x2 equal to lowercase x2 as the unique solution for these two random variables x1 and x2. What is the probability that the random variable x1 will take on the value lowercase x1? And well, that's with probability 1 over p, which we've already seen in the first part of the proof. And similarly, what is the probability that x2 equals lowercase x2? Again, that's going to be with probability 1 over p, and both x1 and x2 are independent of each other, and therefore the probability that both those events will occur is exactly equal to 1 over p squared, which is exactly what we want. So what we have seen so far is that independence itself is expensive and it's hard to get in a computer. So we have relaxed the notion of independence to pairwise independence, or more generally k-wise independence. And in so doing, what we have realized is that we are able to generate a lot of random numbers, random bits, that are pairwise independent and drawn uniformly at random. In fact, we can go even further. So there's a useful extension wherein given two n independent and uniform random bits, we can actually generate 2 power n pairwise independent and uniform strings of n bits each. And in a little while, we will see that this can be leveraged to do sampling using far fewer truly random bits.